We will continue with the membranes. We were talking about peroperation. Let me go slightly more in detail on peroperation. Peroperation is also a membrane process. It is a combination of permeation and evaporation. That means the liquid changes into a vapor phase, it gets permeated through the membrane material, and then on the other side it gets again condensed into a liquid. This is a typical flow sheet of a peroperation process. So you have a feed, it is a liquid feed, it gets vaporized in a heater and then it comes in contact with the membrane. The membrane could be a hydrophilic or a hydrophobic membrane. That means hydrophilic membranes will be used if you are wanting to pull out water from a broth, especially in manufacture of say concentrated fruit juices or concentrated syrups. You do not want any water present inside. Or you can have a hydrophobic membrane. That means if you are interested in separating out hydrophobic hydrocarbons or solvents, then this type of membranes are used. So the membrane could be a hydrophilic or a hydrophobic. Once the feed is vaporized, it gets dissolved inside the membrane, and then there is a diffusion taking place, and on the other side the vapor comes out and gets condensed into the liquid. Now there is a driving force here, you are using a vacuum so that the vapor travels through the membrane. So you can use peroperation for concentrating fruit juices, for concentrating even say ethanol to almost 100%, and removal of solvents and so on. Actually many advantages are there. It requires low temperature and pressure because you are using a vacuum and you just need to put in some heat so that the liquid is vaporized. So obviously the temperature of operation is very low. So it can be used for temperature sensitive material, the energy usage is less. So these are the advantages. Now it is very good for separating out azeotropic mixtures. You know what is azeotrope? Azeotrope is called a constant boiling system. For example, ethanol water is a typical azeotrope. So you can't purify 200% ethanol. So normally what people used to do in the past 100 years, they used to add an entrainer which will break the azeotrope, then they will distill out, remove the water, then again they will distill to remove the entrainer from the water, and the entrainer is recycled back. So it will be a series of distillation column, and you are adding an entrainer and so on. It can't be done for if you want to purify fruit juices because you are talking about a food product. So in such situations peroperation is very good because it will separate the liquid very efficiently. It is very economical for dehydration of organic solvents. That means I want to completely remove all the water present in solvent. So what else can I do? I may use a distillation, that is energy intensive, and sometimes you might not be able to get 100% dehydrated solvent. So what else can you do? You can add some adsorbent which will absorb water or moisture, then you have to filter out that adsorbent, and then the adsorbent have to be heated again so that it gets regenerated and ready for further processing. Okay, so it is going to be 2 or 3 steps. You will be adding an adsorbent like a silica gel or alumina or zeolite. It will absorb all the water present in a solvent, and then you will do a filtration. Now this silica gel or alumina will contain water, so you may have to take it to heater and heat it, so the water gets vaporized, the silica gel is again available, you can take it back again for adsorption. So you see there are so many extra steps, it is going to add to the cost, whereas peroperation is going to be very economical for dehydrating organic solvents. All you are going to use is a vacuum pump and little bit of heating so that the liquid gets vaporized. So we can also use it for organics from aqueous stream. So like if you are using a hydrophobic membrane, and if the concentration of organic present in aqueous is very small, then the organics can be removed from aqueous stream, especially you are talking about waste water. You want to remove some traces amount of organics so that the water can be used for other purposes. Okay, then peroperation is very good. You do not require entrainer, so there is no contamination. I talked about entrainer in isotropic distillation. So there is no contamination, especially in pharmaceutical products or food and healthcare products. It is independent of vapor liquid equilibrium. I hope you all know what is vapor liquid equilibrium. It is the most important principle on which distillation columns are based on. Okay. So distillation, separation of 2 or 3 or multi-component liquids happen because of this vapor liquid equilibrium. So a liquid which has low boiling point will have more vapor present in the gas phase, a liquid which has higher boiling point will have less vapor present in the gas phase. So because of this vapor liquid equilibrium, you are able to separate out in the vapor phase the low boiling component and the in the liquid phase the high boiling component. That is what is called vapor liquid equilibrium. You are not bothered about vapor liquid equilibrium here because the process is permeation and evaporation. So vapor liquid equilibrium does not come into picture here. It can be performed in batch or continuous mode. That means we can do this operation in a batch mode, or continuously you may pass a mixture and continuously you may be purifying the mixture. It is very suited for heat sensitive products, food or pharmaceutical products. So because as I mentioned in point number 1, we are not going to heat it, so there is no question of denaturization or formation of tar or caramel and so on actually. So it is very good for food products and also for pharmaceutical products, because you are not going to deactivate. If there are any proteins present, you are not going to deactivate it here. So the liquid movement here is by the solution diffusion model. So higher flux or higher movement of the solute can be obtained with an increased thermal motion of the polymer change and the diffusing species. Okay. So if the diffusion coefficient of the diffusing species is high, it can travel faster through the membrane. Okay. And if the polymer on which the membrane is made up of, if it has got better mobility, then the diffusion of the solute is also going to be very good. So the polymer on which the membrane, pervaporation membrane is made up of, has a very strong effect on the process, diffusion process. So the polymer backbone makes a lot of difference, the degree of cross linking of the polymer makes a lot of difference, porosity makes a lot of difference. So there is a molecular level interaction between the membrane polymer and the diffusing species. Okay. So you can describe this interaction in terms of Arrhenius equation. You must have all heard about Arrhenius equation a long time back, right. Arrhenius equation comes in kinetics. The kinetic rate constant is a function of temperature and the activation energy, and that is where we might have studied Arrhenius equation. Here too Arrhenius equation comes into play. There is another theory, it is called solution diffusion theory, which is proposed by Graham, on which pervaporation system can be modeled or described. So there is a gas permeation through a homogeneous membrane. This permeation is made up of 3 fundamental basic steps. Okay. So the solute is permeating through a membrane, so there are 3 things that is going to be happening. So solution of gas molecules in the upstream surface of the membrane. So initially you have the solution of liquid which goes into gas, and that gas molecule is in contact with the membrane surface in the upstream. Then you are going to have a diffusion of this dissolved species or solute through the membrane, that is the diffusion. And the third step is the desorption of this dissolved species back into the downstream phase of the membrane. So it will be a desorption of the dissolved species as a vapor, and then in the condenser this vapor is condensed into liquid. So these 3 things are happening. So you are going to have the gas molecules going into solution in the membrane, diffusion of the gas molecules through the membrane, and finally the desorption of this dissolved species back into the vapor phase. So all these parameters affect this pervaporation process, and that is what Graham has proposed, and that is why he calls it as solution diffusion theory. So in peroperation there is always a change of phase, okay. So initially you have the liquid, then goes into vapor, this way, then after diffusion this vapor again goes back into liquid. So there is a change of phase. It is very useful for azeotropic mixtures. You can also use carrier gas. Instead of putting vacuum on the downstream, we can use carrier gas. So the carrier gas can sweep the vapor that is diffusing out of the membrane, okay. So the separation is due to differences in the solubility and diffusion of the species of the membrane. So if some species diffuses very fast, then it will be collected faster on the downstream. If there is another species which is very slow, it will take much longer for it to be collected on the downstream. You need to of course supply heat, that is called the heat of vaporization, for converting the liquid into a gaseous phase, okay, this is obvious. Now the diffusion of this species through the membrane is also proportional to the size of this species, okay. This picture just gives you an idea about the kinetic diameters of various hydrocarbons. Depending upon the carbon number, the kinetic diameter keeps increasing. As you can see, water is very low, kinetic diameter is very small because it does not have any carbon of course. Then you have methanol, ethanol, isopropanol, THF, pyridine, hexane, paraxylene and so on. So you see the kinetic diameter increases from almost 2.5 to 7. So the diffusion of these species is a function of the kinetic diameter. So a species like paraxylene as against isopropanol will be diffusing very slowly because of the size. Yeah, ethanol will be diffusing much slower than methanol because the kinetic diameters are different, okay. Now this is a very interesting book and it gives quite a lot of information about membrane peroperation. It is a review, so some of these studies which I am talking about are collected from this book, and if one is interested to know more about peroperation and polymers and the science and the principles, one can look into this reference. Okay. So when we have peroperation, there is a thermodynamic equilibrium between the membrane and the feed, so we can put in a partition coefficient like your solvent extraction. So you will have a partition coefficient K, which is given by Cm by C feed. Cm is the concentration of the species or solute in the membrane surface, C feed is the concentration in the feed, and K is of course the partition coefficient between the membrane and the feed phases, correct. Okay. Now membrane transport is a rate controlling process and it is given by Fick's law of diffusion. We all know what is Fick's law of diffusion. Fick's law of diffusion connects the flux with the driving force, that is the concentration gradient, and the diffusion coefficient, correct. So this is the Fick's law of diffusion. The permeation flux is equal to minus diffusion coefficient dC by d delta, that means this is the driving force and this is the distance. Now there is a minus term here because concentration will be going down, the driving force is the concentration gradient, so you are moving the solute from a higher concentration to lower concentration, that is why you have a minus term. So you can little bit simplify it, and then we can put it as delta C here, and this distance between the species can be called a delta. We can bring in the partition coefficient also inside. So we will end up having an equation like the flux is equal to dk by delta into delta C. This is the driving force and this is the property of the membrane. So if you look under the property of the membrane, you will see terms like diffusion coefficient, that is diffusion coefficient of the species through the membrane, which is a function of the species as well as the membrane. Delta is like the thickness of the membrane and K is the partition coefficient, that means ratio of the concentration that is just dissolved in the upstream vis-a-vis the concentration in the feed. So these are the properties of the membrane and this is the driving force, that is the flux. Okay. Now we mentioned that it is a function of Arrhenius equation. So we have the permeability and exponent raised to the power EP by RT. EP is the activation energy, R is the gas constant and T is the temperature. So P0 is the permeability constant. Molecular flux, so the solute is diffusing in and reaching the other side, so there is a flux created by each solute. Okay. So the amount of component permeated per unit area per unit time is given by Q divided by A, okay, into T. A is the effective membrane surface area, T is your time. We have put I here because we are talking about ith species, there could be a jth species, kth species and so on actually. So each species will have certain flux. So Ji, the flux, depends upon the moles of component I divided by AT. Now there is some other term which is called perm selectivity. So suppose you have two species I and J, what is the selectivity of the membrane for species I as against the species J, that is what is called perm selectivity. Okay. So how do you define it? We have VIP divided by VJP divided by VIF divided by VJF. Okay. So the I and J represents individual species or components, P represents the permeate and F represents the feed. Okay. So alpha, that is the perm selectivity, is a function of the permeate to the feed, okay, of the volume actually. So industrial applications of pervaporation are now becoming larger and larger. It's been realized that it's got a lot of advantages. So there are large scale installations of pervaporation. So we can use it for treatment of wastewater, contaminated with organic. I am just interested in removing some amount of organic present, not large amount of organic, only very small amount of organic contamination is there and I want to remove it. So pollution control, recovery of organic compounds from process side stream. Sometimes I am doing a reaction, there could be an organic contamination, so I just want to remove that so that I can recycle the process stream. Separation, purification of 99.5% pure ethanol from ethanol water systems. Harvesting of organic substances from fermentation broth. So quite a lot of applications of pervaporations are coming into the market. Now as I mentioned, you can do it in batch mode or in the continuous mode. So obviously the batch mode of pervaporation is very simple, high flexibility. So I can use the same setup for different types of components and so on, but you will require a buffer tank. So you will have a feed tank into which your feed may come in, then you will have the pervaporation system and the product has to be collected in another tank. So you need a buffer tank. In a continuous process you will be using less energy. Why? In a batch process I will be heating, I will complete the pervaporation, I will stop the entire pervaporation, I will charge another lot of material. So you are heating and cooling, so the energy consumption is much higher, whereas in a continuous process you are continuously passing in the hot stream, so you do not have to heat cool and so on actually. So obviously it will consume less energy. It is very good for low impurities in the feed. So I want to remove only small amount of impurity and I have large quantity of this stream. So in that case it is very good. So it is best for large capacity. So large quantity of a stream needs to be processed and it has got very little amount of impurity which needs to be removed using this concept. So nowadays this type of pervaporation is being preferred even for in distillation columns, especially if you have distillation columns systems where you are talking about dissolved solids and so on. So we will talk about how pervaporation can be used in distillation column later in this particular course itself. Okay. Now membranes, let us look at membranes. So as I said, you have two types of membranes, hydrophilic membranes, organophilic or lipophilic membrane, okay, or hydrophobic membranes. Hydrophilic membranes are very good for removing water from organic solutions. That means the amount of water present in a mixture of organic solvent is very little. So I am interested in only removing that water. So obviously you have to have membranes which are water loving or hydrophilic. So polyvinyl alcohol type of membrane, okay, polyvinyl acetate and so on. So these membranes should have glass transition temperatures above room temperature. So the membranes will have glass transition temperatures above room temperatures. Organophilic membranes on the contrary, they allow hydrophobic material. So obviously this is very good for recovering organics from aqueous solution. So I have a very long aqueous stream and there is some organic contaminant. So I want to remove only that. In that situation I need to use organophilic membranes. So these are very good elastomer type of material, polymers with glass transition temperatures below room temperature. And of course you should have membrane bit flexible also, because then organics can pass through, like nitrile, butadiene rubber, styrene butadiene rubber and so on actually. So the organic material can pass through. So two types of membranes depending upon what you want to remove. Do I want to remove little bit of water present in a large amount of organic solvent, or do I want to remove little bit of organic solvent present in a large amount of aqueous stream. Now pervaporation can also be used in distillation, as I mentioned before. You can use it for separating water from a solvent, okay. The solvent could be heavy solvent like chloroform, or it could be a light solvent. So both types of situations we can handle pervaporation. Otherwise you may have to resort to say azeotropic distillation, okay. So let us look at a aqueous light solvent system like this, you know. So you have the distillation column, you are introducing the feed here, and then this is the boiler, the boiler material is being heated up and it is fed up. Now if it is an azeotrope, obviously you will have a constant boiling system, then you will be in trouble, and as I mentioned before you may have to add an entrainer. So instead of that, if you pass it through a pervaporation system, so the light solvent can be removed in the pervaporation membrane and water can come down, okay, and again come down through the column. So the light solvent all the time rises, and then in the membrane you will have something like a hydrophobic membrane, and it will separate out the solvent, so the water will come back. Otherwise if you are resorting to the normal conventional method of breaking azeotrope, we may have to add an entrainer, then again distill, then the entrainer has to be removed, so again distill. So you will resort to 2 or 3 distillation columns. If it is a heavy solvent, the solvent will be in the down and water will be in the up, right. So if it is a heavy solvent, then what do? The solvent will be collected pure, in the top you are going to have solvent and water, again you will have a pervaporation membrane, water alone can be recovered, that means I use a hydrophilic membrane here, and then the solvent which is coming out can be again either mixed with the feed or you can dispose it off. So this type of system is very good for heavy solvents. So the solvent will be collected at the bottoms. This type of system is very good for light solvents, where the solvent is collected at the top and water is collected at the bottom actually. So imagine in a normal solvent azeotropic distillation we may require 2 or 3 distillation columns, whereas here we are talking about 1 column and a 1 pervaporation membrane system. So you are talking about using less equipments, you are talking about using less energy, that is why it is becoming quite useful to have. There is another principle which we need to now introduce, and that is called isoelectric focusing. Now you might have read that proteins have charge. Okay. Why proteins have charge? Because proteins contain acid group, they contain amino group, so you are going to have charge. Okay. Now the isoelectric point is the value of the pH at which the charge on the molecule is 0. Okay. So we sometimes use this particular principle even in 2D electrophoresis also. So we separate based on isoelectric pH. Okay. So we have a pH gradient and each protein will move and it will stop when it reaches the isoelectric pH. Okay. Now all proteins, enzymes, peptides, they will all have amino acids. The amino acids will have both types of positive and negative, so you can have positive or negative type of proteins actually. So in isoelectric focusing, what do? We have the change in pH, and at one particular pH when the protein charge is 0, it will not further migrate or travel. So this principle can be used also for separating out proteins of various isoelectric point. Okay. Now consider a very simple system. I have 3 proteins and protein A has an isoelectric pH at 7, protein B has an isoelectric pH at 6, and protein C has an isoelectric pH as 5. So this is 5 and B has 6 and 7. Imagine I have a mixtures of all these 3 proteins and I am feeding at a pH of 6. So this protein B will not have any charge, that means it will be neutral in this particular pH, whereas the other 2 proteins of course will have charge because they are not in the isoelectric point. So if I apply a large voltage, protein A and C will be moving, agreed, whereas protein B will not be moving. So imagine I have a 3 chamber and I am feeding the mixture of protein at a pH of 6, B will not move, B will just travel down. So I will get a stream very concentrated in B, but on the contrary, suppose I have another chamber where I am passing a buffer of pH equal to 5 and another chamber in which I am passing a buffer of pH is equal to 7, the protein A will move to this its isoelectric pH, and protein C will move to its isoelectric pH. So this chamber will be predominantly A, this chamber will be predominantly C, and this chamber will be predominantly B. So this type of separations based on isoelectric pH can also be achieved. So the separating chambers are made up of membranes. Okay, so these membranes will allow these proteins to migrate towards its isoelectric pH. Okay. So this is another way of separating out proteins having different isoelectric pH actually. But this is not a very popular type of large scale separation process, you know, but it can be used in a small scale in laboratory settings. But the main principle here is based on isoelectric pH. Proteins with the charge becomes neutral at its isoelectric pH. So when they have charges, when I apply a voltage, they will be migrating until it reaches its isoelectric pH. So proteins will be located in their respective isoelectric pH, and that principle is used in this type of separations. So each protein has a different isoelectric pH. In fact, this table tells you that. Look at gelatin. No, it has got a very high molecular weight material, its pH is 4.8 to 4.85. Insulin 5.3 to 5.35. Cytochrome C 9.7. Myoglobin 7. Urease 5 to 5.1. Hemoglobin 6.79 to 6.83. So you see a difference in their isoelectric pH. So I should be able to make use of these differences in separating out. Of course you need to keep in mind if the differences are very small, you might not be able to really achieve such fantastic separations. If the differences in isoelectric pH are large, then I may be able to achieve the separations very efficiently or effectively. So you need to keep that particular point in mind actually. Okay. Look at the difference in molecular weights of these material, you know, gelatin very large molecular weight, myoglobin 17,000, cytochrome C 15,000 Dalton. Okay. So the molecular weight differences are pretty high. Now the problems are there in isoelectric focusing. Okay. There is always going to be remixing of purified materials with semi purified materials or crude starting materials. So there is always going to be that. There is going to be heat generated quite a lot because you are applying a large voltage, so heat is getting generated, so you need to cool it, otherwise the heat generated may denature your protein. That is a point you need to keep in mind, you know. Membrane bioreactors, that means a combination of a bioreactor with the membrane. So what are the advantages? I can use the membrane for separation, the bioreactor for the bioreaction, and I can combine membrane and bioreactor together. So it is like telescoping. I just have one system which will do the reaction come separation. So I will not require a reactor, I will not require a separator separately. Okay. So let us look at a membrane bioreactor. So I have a reactor, I do the reaction and then I go through a membrane setup. So there is a permeation taking place and the remaining material which is not permeating through is fed back into the reactor. Where do I use this? I can use this for, suppose I am doing a biotransformation and I am having whole cells or enzymes in the reactor. I want to retain the enzyme or the biological molecule like bacteria or fungi, but I want to remove only the metabolites, products. So what I can do? I can do the reaction continuously, I can pass it through the membrane system, so the small molecule or metabolite will permeate through, then I can recycle the enzyme back. Okay. So I can do this operation continuously. Where do I use this? For example, I have a fermentation where I am producing alcohols like ethanol or butanol. Now they are not, the microorganisms are not very tolerant beyond a particular concentration. So in a normal conventional fermentation we just stop the reaction, but if I have a membrane I can continuously remove part of the alcohol that is produced and the remaining active biomass can be sent back. So the advantage is the concentration of the alcohol will be much lower all the time in your reactor. Okay. So that is the main advantage of this type of setup actually. So continuously I remove the alcohol that is produced, so the concentration of alcohol in the reaction media is very small, so I can be rest assured that the microorganism or enzyme is not going to get denatured because of the build up of the alcohol. So I am not allowing the alcohol to build up. That is one design. Another design, I can have the membrane itself as a active catalyst, that means I can immobilize my enzyme in the membrane. Suppose I am doing a biotransformation using enzyme, instead of immobilizing it on a glass bead or encapsulating it on alginate or so on, I can immobilize it on membrane itself. So the feed, when it comes in contact with the membrane which contains my enzyme catalyst, it will get reacted and the product will permeate through and go out. Okay. So the enzyme itself is immobilized on the membrane material. So the advantage is I do not have to have a separate filtration unit for filtering my enzyme and again putting it back into my bioreactor and so on. So I can avoid the second operation of filtration. That is the advantage of the combination of membrane bioreactor here. So the first design we saw where we are continuously removing a metabolite or a product so that you do not allow it to build up. If you allow it to build up, you may be denaturing your bacteria or fungus or enzyme. The second design is you are immobilizing your enzyme itself so that the membrane becomes a active catalyst and the product is removed continuously as a permeate here. So these are the two different designs by which I can achieve tremendous flexibility with the help of a membrane into the bioreactor technology. So both are alternate. So I can have the first one, I can have a traditional stir tank reactor and then I can have a membrane separation unit. In the second one, the membrane acts as a support for the catalyst. Catalyst is your enzyme or active cell, okay. And then separation also automatically happens because it is immobilized on a membrane. So your metabolite may be just diffusing through or permeating through. So by choosing your membrane, we can achieve this type of permeation or diffusion or filtration type of process. So the biocatalyst can be flushed along a membrane module, it can be segregated with the membrane module, it can be immobilized in or on the membrane by entrapment, jellification or physical adsorption or ionic binding, covalent binding or cross linking. So all these can be achieved and you will have the membrane acting as a support or immobilizing support. So what are the advantages? We can increase reactor stability, we can increase productivity, we can have improved product purity and quality, we can have reduction in waste, the product can be continuously removed. So if the product is toxic to the biological molecule or it is an inhibitor to the biological molecule, by continuously removing it we are preventing its accumulation. So the efficiency of the overall system will depend upon the biochemical, that is the catalyst activity, reaction kinetics, concentration, viscosity of the substances, product, immobilization stability, how stable is this enzyme when it is immobilized on your membrane. That is a very important point to consider because enzyme may lose its activity when you are trying to immobilize it on the support. The geometric parameters, the membrane configuration, is it a flat plate, it is a tubular and so on, the morphology and also the pore size distribution. Then of course the hydrodynamic parameters such as the pressure, the flow, the velocity, so all these parameters come into picture. So the overall efficiency of this type of immobilized systems will be biochemical related, geometry related and hydrodynamic related. So they are used in a hollow fiber configuration. You can have a hollow fiber and your enzyme could be immobilized inside of the tubes. So we can have a very high packing density, that means large surface area per unit volume. They have been already being used in production of amino acids, antibiotics, anti-inflammatory compounds, anti-cancer drugs, vitamins, optically pure enantiomers and so on actually. So a lot of applications are slowly coming up in the market and I think it's because of its advantages they will be replacing quite a lot of the conventional reactor followed by separators actually. So there are examples of synthesis of lovastatin with the immobilized Candida rugosa lipase on a nylon support, production of liltiazem chiral intermediate using a multi-phase enzyme bioreactors, synthesis of certain oligosaccharides and oligodextrans in a recycled membrane bioreactor, production of derivative of analgesic quercetin using alpha chymotrypsin as catalyst and alpha alumina mesoporous tubular support as membrane, biodegradation of high strength phenol solutions using Pseudomonas putida using a microporous hollow fiber membrane. So a lot of applications are already being investigated. Another area where membranes have come into being, I would call it much more recent, is the membrane chromatography. Unlike the normal solution based chromatography. Okay. So membrane chromatography, it's an alternate to conventional resin based chromatography, you know. So what are the benefits? It's shorter diffusion time when compared to resin based chromatography, because the interaction between molecules and active sites on the membrane is through convection, that means flow, whereas in a normal chromatography there is a stagnant fluid inside the pores of a adsorbent material or particle. So the diffusion coefficients are much slower, so the diffusion times are much larger. So adsorptive membranes, they have the potential to maintain high efficiencies because you can use high flow rates, we can use it for large biomolecules with small diffusion coefficient. So by doing this short diffusion times, we are preventing the protein degradation or even denaturization of the proteins. So it is ideal for biological molecules. So you have stacked membranes, we have hollow fiber membranes, you can have spiral wound membranes for membrane chromatography. In a normal absorptive mechanism, you may have ion exchange, hydrophobic, reverse phase, affinity based procedures. So we can use all these procedures for adsorption of the active ingredient on top of the membrane material. Okay. So you have the active ingredient sort of immobilized on the membrane material, and this type of immobilization can be achieved through different mechanisms: ion exchange, hydrophobic, reverse phase, affinity based procedures actually. So ion exchange membranes, there will be strongly acidic groups like sulfonic acid, or it can be strongly basic groups like quaternary ammonium. It could be weakly acidic like carboxylic acid, or weakly basic like diethylamine types actually. You can also have affinity membrane, so you will have ligands such as immunoaffinity ligands, protein A and G, low molecular mass ligands like cibacron blue, histidine, tryptophan, and other ligands like copper 2+ and so on. So we can also have affinity ligands immobilized on membrane, so we will get a affinity membrane type of systems. So what type of membranes we can use? Cellulose based material, polysulfone based material, polyamide based material, hydrocide. We can also have composite membranes, you know, such as blends of polyether sulfone, polyethylene oxide coated on all surfaces with covalently bound layer of hydroxy ethyl cellulose. So we can have different types of membrane surfaces: polymeric, natural materials, hydrophilic, as well as the hydrophobic. So commercial membranes, flat sheet systems, there is a company which is manufacturing that. We can have stacks of membranes, several company in Europe and US, radial flow cartridges, hollow fiber modules. So different morphologies or different systems and different companies which manufacture these commercial membranes. So how does a membrane chromatography and gel based chromatography look like? We are all familiar with the gel based or the liquid chromatography. So you have a particle is nothing but a support, then we will have the ligand molecules here, and then we have the solute which will get in contact with the ligand. So you are going to have film diffusions, you are going to have pore diffusions, and then you have the binding kinetics. Whereas in a membrane system, if you see, you will have the membrane and then you have the ligands attached to the membrane. Okay. So here we do not have pore diffusion coming into picture, so you will have film diffusion as well as the binding kinetics. So you are getting rid of the pore diffusion, so that is one of the main advantages of this. So diffusion times will be much smaller, much shorter. So a lot of examples have been quoted where membrane chromatography has been used vis-a-vis the conventional liquid phase chromatography. So membrane chromatographies have been reported for compounds such as proteins like monoclonal antibody, serum albumin, enzymes, or DNAs and viruses and so on actually. Of course they have still not come into large scale commercial operation, but they are still in the lab, but they seem to have quite a good advantages when compared to the conventional chromatography, where we are talking about standard stagnant liquid film. So you are going to have different types of diffusions coming into picture, which will slow down your process. Applications of membrane processes: theophilic membranes for the purification of monoclonal antibodies from cell culture, immobilized L-histidine in hollow fiber membranes for the separation of immunoglobulin G from human serum, ion exchange membranes for the isolation of antibacterial peptides from lactoferrin, cation exchange membranes for the purification of alpha viruses, anion exchange membranes for the adsorption of DNA, and strong anion exchange membranes for reduction of endotoxin in a protein mixture. So a lot of applications have been reported using membranes for separations. Okay. So different principles like ion exchange principle, ligand based principle, all have been exploited. So membrane separation processes are used for separating mixtures by using thin barriers. It is a synthetic material or it is a natural material. So we are separating two immiscible fluids. The driving force in a membrane process is concentration gradient, pressure gradient. So there is going to be a transport of one or more feed components. Okay. So we looked at a large number of membrane separation processes over the past few classes. Some of them have pores, fine pores, some of them do not have pores. So the process is like a diffusion. The processes which are based on pores is like a filtration. Okay. So we have microfiltration, which is almost exactly like your filtration. Then we go to ultrafiltration and nanofiltration. Then we looked at reverse osmosis, which is trying to overcome the osmotic pressure. So you are applying a large pressure so that the solvent flows out pure. Then we looked at dialysis, that means movement of ionic material, ionic proteins or ionic salts. Electrodialysis, where you are applying an electric field, so the cations and anions move to the respective electrodes. Again dialysis is used quite a lot in artificial kidney for removing salts from blood and purifying blood, and electrodialysis is used again for separating out salts from protein mixtures. Then we looked at perevaporation, very ideal system for removing small quantities of water from a solvent or small quantities of solvent from an aqueous stream. It just uses nominal temperature and vacuum, so the energy consumption is very low when compared to the normal distillation type of approach, and perevaporation is very good if you are talking about temperature sensitive material. Then we looked at isoelectric. So all proteins have isoelectric pH at which the charge on the protein is 0. So you make use of it and you separate proteins of different isoelectric pH using a pH gradient. Then we looked at membrane bioreactors. So where you are combining extraction or removal or filtration of the metabolites in a fermentation broth, but simultaneously carry on your fermentation. So you are combining two things, the fermentation or biotransformation with separation. Then you can also immobilize your enzyme on your membrane. So you can again get the advantages of the enzyme as well as you can get the advantages of the separation of the metabolite. This is very good if you want to continuously remove a metabolite which could be toxic, which could be inhibiting your biocatalyst or biomass or enzyme or okay. So membrane bioreactors are extremely useful in that area. Then we looked at membrane chromatography as against the conventional liquid phase chromatography, where you have the ligands covered by liquid. So you are going to have the diffusion slowing down the entire process. The diffusion times are much larger when compared. Here in a membrane chromatography, the ligand is immobilized on the membrane surface, so the diffusions are much faster. So I can have ion exchange, different types of cation membranes, anion membranes and so on, or ligand based membranes where I am immobilizing an active ligand on a membrane surface. So we achieve very fast diffusions, we achieve very high separation rates, but membrane chromatography is of course is still in the early stages, whereas if you look at the filtrations like a micro ultrafiltration is well established, reverse osmosis is also well established, dialysis, electrodialysis is also well established, peroperation is also well established. Isoelectric focusing is more in the lab scale. Membrane bioreactors are already in the market in much commercial scale. So you see, membranes have a tremendous application and use in downstream, where you are handling small molecules, where you are handling organic solvents, organic chemicals, where you are handling biological molecules like proteins or enzymes. Okay.